Excellent start. All right then, everybody, good afternoon. How are you all doing? Is this all we got? Just 4 of you? All right. You're gonna have to pick up the slack and be extra loud then. Okay. Oh, Ariel's made it. Okay, good. Now we can begin. Before we get started with the super awesome mathematical content for today, and it is pretty great stuff, there are a few announcements to go over. Since we are getting towards the end of the year, there's some critical things I need to remind you of. First and foremost, remember, well, you're all online anyways, but all classes will be online next week, Monday, Tuesday, and Wednesday. Wednesday itself is a half day, so class will be over by noon, which means each class period has been reduced to 30 minutes. Okay, check the sent out schedule for that. It's also posted on my Discord. I've scheduled for our class specifically to be a work day / catch-up day for that time. So you'll have all the same workload as any other week. You'll still have that week's homework online. You'll still get the SAT practice that morning. You'll still have Mondays and Tuesdays classwork. If you didn't finish that before, you could finish that then. Okay, so any of that's viable. Just work on that for that day. But you'll still need to check in with me on Zoom. I will be extra remote. I'll have already gone to my folks' house for the holiday, so I'll be tuning in from there. So I'm just going to take attendance, see that you're working, and you carry on for the rest of the day, okay? And again, if you finish stuff then that day, then you don't have to worry about it for the rest of the holiday, okay? And then later, at the end of the year, we of course have a final exam. As usual, nothing has changed there, so the schedule, the actual test times for each class is put on my master schedule, so you can just check that one place for that information. And then the week before that is all review. So we'll have a review packet, we'll work on that in class all week up until the last day of that week, which for you guys would be Wednesday there, where we will have a review, I'm calling it a quest, because it's a quiz test. So you'll take it just like a quiz is, that's the format, but it'll go in the grade book as a test category of points. So it's worth a whole lot. It can have a big impact on your grade. But because it's a quiz is, you can retake it as oftentimes as you need to get the grade that you actually want. So my hope is that you take advantage of that to actually improve your grade. This is a huge opportunity for some of you to get some major points back. But history has shown that not all of you go to the effort of redoing your quizzes to 100%. So this would be the time to do it, okay? So please, please, please make best use of that opportunity. Don't squander it. All right, any questions on any of those announcement items? No? Okay. Then let's go on to today's fabulous topic of the Pythagorean Theorem. Yeah, this is where the soundboard comes in handy. I need a cheering, because this is like the #1, possibly the most well-known math theorem out there. Definitely the most well-known geometry theorem. Many of you have probably already heard it before. Okay. For any right triangle, emphasis on right triangle, this only applies to right triangles. If you call the sides A, B, and C such that C is the hypotenuse, Pythagorean theorem says, anyone know the equation? Oh, come on, there's got to be at least 1 in 5 of you here that knows it. Oh, Ariel's got it there in chat. a squared plus b squared equals c squared. Very good. Oh, if I can actually draw a plus, there we go. Excellent. It sounds super simple, and it kind of is, right? What this allows us to do is, so long as we know it's a right triangle, we can take any two sides of our triangle and find the third side. The most straightforward would be finding the hypotenuse c squared, since it's already equal to. But you could solve for any of the others. All you got to do is subtract one of them over. Let's try a quick example here. Give me two numbers. Any two numbers. Let's keep them reasonable. Two numbers between 1 and 10. What's that?
16 and 36.
You say 15 and 36?
I said 16, but 15 is okay.
All right. 15 and 36, here we go. You would do that, wouldn't you? All right. We can make it work. So, we still have a squared plus b squared equals c squared. Find that third side of our triangle. So we need 15 squared plus 36 squared is going to be our c squared. 15 squared is, ooh, anyone know this? 225, double check me. Plus 36 squared is 6, 3, 6, 7, 8, 9, 6, 1296. That's equal to our c squared. So now we add those together. You're really making me work for it. All right, add those up. 2, 2, 5, 6, 5, 11, 9, 10, 12, 5, 1, 15, 21 equals our c squared. And so then you have to solve for actual c by itself, so we square root both sides. So the square root of 1521 equals c. And that's in exact form. I don't know square root of 1521 off the top of my head, but I do have handy dandy calculator. We can check it here. 1521 square root. Pebble tile shop. No, excuse me, trying to do math here. Is, oh my gosh, it worked. That's a perfect one. Look at that, 39. Did you know, Brian, did you know this would work out? That's pretty cool.
Yeah.
Look at that. All right. So there you go. Equals 39. So there's our final answer. Of course, whatever units, inches, or centimeters, if that's applicable, right? That's how you use the Pythagorean theorem. First and foremost, solve for the third side of a triangle. And this becomes incredibly powerful, incredibly useful, because triangles are everywhere. Okay. Any questions there so far? Because that's the basic idea. But there's a few more interesting notes that I want to highlight about the Pythagorean theorem as we go here. So first up, yes, Pythagoras was a Greek mathematician. That's what it's named after, but it wasn't actually the first one to discover it. We found evidence from Chinese civilizations. They knew about this. We found evidence from ancient Egyptians. They knew about this. Lots of people understood the relationship. In fact, the ancient Egyptians made use of this to form a right angle from a piece of rope. Okay? You may remember the Egyptians are very famous builders, right? Fantastic pyramids, perfectly square. All right, the precision of their stonework and the geometry is seemingly incredible. And we're like, how did they do this so precisely? Well, they didn't have modern tools and measuring techniques. They just used a rope. Think about that. How can you use a rope to create a right angle? All you can do is pull it taut into a line, right? How do you make sure it bends and stays put that way? Well, give you a hint. We're going to need to make a triangle, right? That's what this is all about. So first thing you got to do is loop your rope together, tie it up into a loop, and then you get 3 guys to pull on it. So one pulls this way, one pulls that way, one pulls that way. And so when they pull this taut, if they do it just right, they end up with a triangular piece of rope, right? There's the knot tied in the middle. And to make sure that this comes out as a perfect right triangle, what they would do is they would actually have additional knots tied into this thing, evenly spaced along the rope, which I'm not quite drawing perfectly here. You'll have to excuse my crude drawing. 1, 2, 3. Whoops. We got too many there. 1, 2, 3, 4, and we'll get rid of this extra one here. Okay, so you put these extra knots in the rope such that you get 1, 2, 3 segments in between each knot on this side, and 1, 2, 3, 4 segments on this side, and 1, 2, 3, 4, 5 segments on this side. And if you do that, 3 squared plus 4 squared equals 5 squared. I'll let you double check the math on that one. Makes it a right triangle. So they were able to use this knotted piece of rope to create a perfect right angle. Okay? And then from that, they can then compare that to the stone or the bricks that they're laying and make sure they've lined things up. Just hold the rope next to or above it. Say, okay, yep, that fits in there. Okay, there you go. Right? And so it's like having a carpenter's square really handy before they had, could forge it in steel and make sure it's perfectly straight like that. So that's how they did it, which is actually using the Pythagorean theorem backwards. Instead of saying, if it's a right triangle, then 3, 4, 5, they're saying, reverse that. If I make 3, 4, 5, I know it's a right triangle. Which brings us to the next point. The converse of the Pythagorean theorem is also true. As I was saying, instead of if right triangle, then a squared plus b squared equals c squared, we could say if a squared plus b squared equals c squared, then the triangle is a right triangle. That's pretty handy because it gives us a really quick, efficient test of checking whether or not any given triangle presented is a right triangle. And we don't have to break out the protractor and measure the angle, but this one's only 91 degrees, right? We don't have to do that. We can say pretty equivalent. Just give me the side lengths, and I'll tell you if it's going to work out to be a right triangle or not. It's really nifty. Okay, any questions so far? No? Then I have one last major point to add onto Pythagorean theorem, and that is the Pythagorean triples. Okay? It seems like we got lucky with our first example, that it came out to be a perfect integer. We could have been, square root of, right, anything else. Well, 1521, if it had been like square root of 1520, that'd be some crazy decimal, right? It wouldn't have worked out perfect. So it turns out there's a limited set of integer triples that will fit the Pythagorean theorem. 3, 4, and 5 being one of the most well-known. But there's also 5, 12, and 13. There's 7, 24, 25, 8, 15, 17. All of these work out with no extra decimals tagging on the end, you can take that square root of that final number and expect a nice integer value. In fact, they're so common, we've seen one of these before. Anyone recognize that 7, 24, 25? Yes, ladies and gentlemen, it is from our volume practice. I told you these were going to make a comeback. So this was it. This was the solution. If you weren't sure how to get the height of your cone, knowing the radius and the diameter and slant height, half the diameter to get the radius, that's one leg of your triangle. The 25, that's the longest side. It's the one opposite the right angle. Therefore, it is the hypotenuse. That's my c squared. So I could run the numbers and say, okay, 25 squared minus 7 squared is whatever, take the square root of that and get my answer. But if I recognize that I have 2 out of 3 of one of the Pythagorean triples, I don't need to do the calculation. I can just go straight to the answer. 7, 24, 25 fits together. And that's how I originally approached that myself. So there is great power and a great shortcut in committing these guys to memory. It's going to save you a lot of time, especially on the SAT, because they love these numbers. The SAT absolutely adores them. They are their favorite numbers. There's always going to be at least one triangle on the SAT. That's a guarantee. And if there's a triangle on the SAT, odds are it's most likely a right triangle. That's the most common type of triangle on the SAT. And the most common type of right triangle they have is a Pythagorean triple. And the most common Pythagorean triple is the 3, 4, 5. They're consecutive like that. It's beautiful. It's wonderful. It's easy to remember. 3, 4, 5. Triangles have 3 sides. Perfect Pythagorean triple. 3, 4, 5. Just count up from there. But these next ones, probably in descending order, right? This is the most common, second most common, third, and fourth. And there's more out there, of course. We stumbled upon one ourselves earlier. Or is it a unique one? Because it's not just these guys. We can also find multiples of them. I would say the 3, 4, 5 structurally is the most common triangle on the SAT, but it's usually not presented as a 3, 4, 5. More commonly, what they'll do is they'll double or triple all the numbers. You can go like, you might see a 6, 8, 10, or 9, 12, 15, right? You could, if you multiply all 3 of them by the same number, you are just scaling up your triangle, just to make it bigger, but you keep that proportion intact. Okay, so it's still a Pythagorean triple, still a right triangle. Okay, and let's see, was this one of those? Do these share? Let's see, if I divide by 3, I get 5. Divide by 3, I get 12. Divide by 3, I get 13. 5, 12, 13. Look at that. I should have known that it was going to work out. See? Could have saved ourselves a load of time. All right. Any questions there on Pythagorean triples? At the very least, put this list in your notes at the top of your page somewhere so you can have a handy-dandy reference until you lock it in place. And then I will leave the rest up to you. You have these 10 exercises to tackle based on the Pythagorean theorem and its application in other realms. Lots of things can be broken down into triangles. Right? For example, this guy, knowing these coordinates, can you work out what the x and y coordinate has to be to make C? And then, hey, look, I made a triangle. Now I can find, these sides are really easy. It's just simple subtraction, right? And then Pythagorean theorem to get that distance, right? 8, don't let 8 fool you. Do not get caught up in these triangles in the middle here. Keep everything as a right triangle. Hey, you know RS. Use that to work out this hypotenuse. And then that gives you this length and that length, and now you have the long right triangle. Use that to find the longest one, right? Keep working out, always right triangle to right triangle to right triangle. And number 10 is a pretty good one, but not super tricky. If you're overthinking that, you're going at it too hard. Keep it simple. It won't be too bad. Right, but other than that, that's all the hinting I'm going to give you. The rest I leave to you guys. So I'm going to stop the stream here. But if you do have any questions, feel free to let me know. I'll see what I can do.